The safety paradigm of a high temperature gas cooled reactor is different from a conventional light water reactor, and hence there's a need of a separate study for safety domain of high temperature gas cooled reactors. Hi, I'm Ankit Mishra and I shall be presenting on very high temperature gas cooled reactors, commonly known as HTGR or VHTRs. Let's talk about some of the design features. The characteristic difference between any other nuclear generating technology and HTGRs is the use of coated fuel particles. This supports high temperature, typically in the range of 750 to 1200 degrees centigrade. Helium is used as coolant and graphite as a moderator. According to International Atomic Energy Agency, any reactor with output of less than 300 megawatt electrical is known as small reactor, and if the reactor are made on an assembly line and can be transported to the site using rails, roads, etc., then they are also known as modular, hence small and modular. The typical power density is 3 to 6 watts per cubic centimeters as compared to 60 to 100 for a conventional light water reactor. HTGRs come two basic designs, prismatic block type and pebble bed type. Let's have a look at the TRISO particles. The diameter is roughly 0.92 millimeters, which is 1/10 of a centimeter. The innermost layer is fuel particle made either out of uranium dioxide or uranium oxycarbide. Then it has a buffer low density material which has enough room to absorb fission products. It is followed by another layer of high density silicon carbide layer. The outer layers provide robustness and structural integrity to the coated fuel particle. All the outer layers but the fuel kernel are made out of isotropic pyrocarbon and has different densities as illustrated in the picture. In prismatic block fuel, the TRISO particles are embedded into fuel compacts which has 26 millimeters and 10 millimeters as inner and outer diameter respectively and a height of about 39 millimeters. These are put together to make fuel rods. These fuel rods are put into a graphite tube in the graphite fuel block. Graphite blocks stacked one over another make up fuel column. A typical fuel block is seen in the image and gives an idea of the relative dimension. Fuel blocks are designed in such a way that heat can be removed from the block efficiently. For this, some of the guide tubes are reserved for coolant flow. Pebble bed type HTGR fuel. Here again, the same TRISO coated fuel particle is put into graphite dough and then hard pressed into balls. It is then surrounded by a 5 mm thick graphite layer. The diameter of the resulting fuel ball is 60 mm or 6 cm, roughly equal to a billiard ball. If we look closely at the pebble bed vessel, it is elongated typically to support natural convection with lower diameter to assist a radial conduction. The fuel pellets are dropped inside the vessel from the top and removed from the bottom of the vessel. Again, after brief inspection of the fuel integrity, these fuels can be reloaded. The design allows for the support of online refueling. This online refueling is typical of CANDO PHWR, where fuel assembly in cylindrical calandria is irradiated and shuffled both axially and radially. This helps in increasing the burnup. For heat transfer, cold helium at 60 megapascal, which is roughly equal to 60 atm at STP, is fed from the top and hot helium is collected from the bottom of the vessel. This hot coolant goes to the reactor generator. Let's talk about the benefits of HTGR technology. Since we have higher outlet temperature of 700 to 1200 degrees centigrade, the efficiency of electricity generation increases. This also competes in full market of electricity and process heat. As an example, we can use process heat or process steam for petrochemical industry and also hydrogen production. This is known as cogeneration. The system also features significant improvement in safety and thus allows less stringent preparedness or emergency preparedness. Decay heat removal can be done by natural means as there is no possibility of core meltdown. Radioactivity is contained within the coated particles. Relaxation in emergency preparedness zone, which can now be at the site boundary. The system can achieve a higher burn up of about 80 to 200 gigawatt days per ton of heavy metal. There is flexibility in the fuel cycle and this can burn plutonium very efficiently. Let's talk about the challenges. As already mentioned, it has lower power density and hence this implies that the reactor vessel would be large. Typically, it is of the order of 2 to 3 times that of a normal LWR reactor vessel. There is also a limit due to the forging capacity of bigger reactor vessels. Helium coolant has low density and hence requires high pressurization. This gives rise to the need of a reactor pressure vessel instead of a reactor vessel. This adds to the capital cost. Coated fuel particles costs are expected to be higher and hence this also adds to the cost of the fuel during operations. Let's now talk about the safety paradigm of this type of reactor employing TRISO coated fuel particle. As the first line of defense in DID, we want to retain the radionuclides inside the coated fuel particles. We would like to control the heat generation, remove the heat from the core, and control chemical attack. We rely on the functional containment of the fission products and fission product gases. Uranium dioxide and uranium oxycarbide kernel is surrounded by carbon buffer, which is porous and hence absorbs what comes out of the fuel kernel. Then there are 3 other carbon layers to give stability and enhance the integrity of the particle. Then we also have prismatic and billiard balls to contain the fission products which escape the inner layers. In this slide, we also see a graph between fuel failure fraction and the fuel temperature, which has been found empirically by experimentation and also combining it with analytical models. It is very obvious that while the normal operating range does not exceed 1200 degrees centigrade, there is no fuel failure chances till 1600 degrees centigrade. This is the limit or the maximum design basis event temperature. Beyond this, there is a slight increase of fuel failure probability capped at 10% till 2300 degrees centigrade before taking nearly vertical flight at 2400 degrees centigrade. Let's talk about the reactor cavity cooling system. The picture on the right describes the mode of heat transfer. Within the core, the primary mode is conduction. From the vessel to the RCCS cooling panels, it is radiation and free convection in the reactor cavity. We also see a spot where the cold outside air comes down under gravity after heating up, naturally rises and thereby creating suction in the system. This system operates even during normal operation of HTGR and results in loss of about 1% of heat. The inherent safety feature is associated with this system is a product of higher negative temperature coefficient of reactivity, lower power density, and moderator properties. Let us now look at the loss of flow accident simulation exercise. We see 3 things. First, under depressurization condition, the maximum temperature reached is about 1680 degrees centigrade with a mean of about 1600 degrees centigrade. Second, the timings it takes is about 40 to 50 hours to reach this maximum value. Third, due to negative feedback, the temperature starts to dwindle. In the other figure, we see that normal operation under pressurized condition, maximum temperature reached is 1200 degrees centigrade. Then we have depressurization, where the maximum temperature reaches 1600 degrees centigrade. This also sets the design goal for the maximum design basis scenario at 1600 degrees centigrade. Now, taking a look at all the different slides together, we see that fission products are contained and particle failure is independent and is driven by the maximum temperature only. There is passive cooling feature. Third, the fuel particle is safe with zero probability of failure till about 1800 degrees centigrade, beyond design basis consideration. The negative feedback along with other favorable conditions keep the reactor temperature in check even in case of a LOCA or a LOFA. More on safety terrain. We have understood so far that it's a different system altogether, and hence fundamentally and it is fundamentally more forgiving and gentler. Fuel failure mechanism of coated particles are decoupled and totally independent, which means one coated particle failure cannot lead to failure of neighboring coated particle, as failure is a derivative of the maximum fuel temperature. Failure has no impact on the coolability of the fuel. Coated particle failure will release a minuscule quantity of fission product. Note, based on the inherent safety features, there is no cliff edge effect or large releases even in an extremely rare event far beyond the design basis scenarios. Is this a new technology? Of course not. We have seen several experimental and commercial operations since 1960s. We have extensive operational experience. The technology is mature and is ready for deployment for temperature up to 850 degrees centigrade. We have well-documented know-hows on various aspects. Knowledge base is intact. Let's look at the R&D initiatives. Materials. We require high temperature withstanding materials. We also need to figure out more applications so as to benefit from the technology in hand. International Atomic Energy Agency has published various TechDoc series. Some of them are mentioned on the slide. There is also a test facility at Oregon State University. IAEA with Research Center ULEC has made available HCP, that is HTGR code package, to all member states under ONCORE, which is IAEA Open Source Nuclear Code for Research Analysis Initiative. IAEA is also open to various CRPs, that is collaborative research projects with various universities and research institutions across the globe. Before we conclude, let's do a quick comparison of the standard conventional LWR with the HTGR. The moderator and coolant are graphite and helium. In case of LWR, we have water. Average exit temperature is 700 to 950 degrees centigrade. For an LWR, that is 310 degrees centigrade. Structural material is again graphite. For an LWR, that is steel. Fuel clad is silicon carbide and pyrolytic carbon. For LWR, that's zircaloy. Fuel, we can use either uranium dioxide or uranium oxycarbide. For LWR, we use UO2. Now, fuel damage at time at temperature. So for UCO, it's 150 hours at 1800 degrees centigrade. For LWR, there is no time limit. So it can happen as quick as in seconds. And the temperature for fuel failure is 1260 degrees centigrade. Power density is 4 to 6.5 watts per cubic centimeters. In case of LWR, as we had already seen, this is 58 to 105, which is like 20 times higher. Migration length is about 57 centimeters because of the low density of the HTGR fuel, and for LWR, that is 6 centimeters. Thank you. If you have any other questions or comments, you can email me at ankit.nuclear@gmail.com.